Hi everybody, I'm going to go over a couple of carboxylic acid reactions in this video. So these are going to be the most common carboxylic acid reactions that we're going to run into. There's a few others out there, but we're not going to focus on them in class. You'll probably see them if you end up moving forward. But these ones are really big ones, very highly used. So we have one with thionyl chloride, which we've seen before in terms of chlorination when we were doing alcohol reactions. So we're going to see a very similar type of mechanism with that today to get an acid chloride. So that's really, really helpful because you can go from, you know that you can get the carboxylic acid from any carboxylic acid derivative, and then you can take that carboxylic acid to an acid chloride where you have a really wide range of functionality afterwards. So from the acid chloride, you can pretty much make any of the other carboxylic acid derivatives, which is really, really helpful. So that is a really, really good reaction to have in your pocket. The other one is this side, which makes an ester. So this is actually called a Fischer esterification. This is a named reaction, and it just uses some type of alcohol, it doesn't matter what. And then an acid, it has to be kind of a non-nucleophilic acid. So sulfuric acid is a really good choice, pretty common choice for that. And then you get an ester out. So again, that's really helpful just in terms of, if you want to kind of hide that acidic proton briefly, that would allow you to do that, and then you can hydrolyze it again, or if you really just want to make an ester, there's that option too. So let's go ahead and look at the mechanisms of these two. Again, we should see very similar types of processes compared to our other carboxylic acid derivative reactions. Oh, oops. Wrong way. Okay, carboxylic acid, there we go. And we're going to get to acid chloride. All right, so the first step, we've got thionyl chloride. Okay, when we're working with thionyl chloride, we should be thinking about it as if it was a carbonyl. Obviously, it doesn't have carbon, but that sulfur-oxygen double bond is going to function in a very similar way. Okay, so we're going to use one of the pi bonds. And keep in mind, I'm doing this arrow just to stop myself from having a carbocation here. If you want to do the carbocation and then show a resonance structure of it, also totally fine. I'm just doing both of the steps in one. All right. Oops. Helps if I have the right connectivity. There's oxygen there. Okay, so then I end up with something like this, where I've attached this oxygen to that sulfur atom, and I've got a positive charge on my oxygen now. So at this point, this is essentially a tetrahedral intermediate over here. So I can have my lone pairs come down and kick off one of my leaving groups. So in this case, it's chlorine. But the reason I have the reversible arrow there is obviously you could imagine this being a pretty good leaving group as well. But this direction with the chlorine leaving is how we're actually going to move towards the product. So I am just going to have the equilibrium arrows here until we get to the end, which is when we have our irreversible step. Okay, so then we get to this group. Move that box so I can actually see it. And we've also made Cl- here, okay? Okay, so now I've got my Cl-, so that's actually going to be my nucleophile now. And I'm going to use that carbonyl as my electrophile. So we're going to go attack right there. Move the electrons up. And then I get to this intermediate. Again, I'm kind of at a tetrahedral intermediate type stage. So I can have my lone pair move down and then kick off this whole thing. So this is actually a very, very good leaving group, and we'll see why in just a second. Okay, so if I have those two things, I've got my O plus with my chlorine on it. So it's just a protonated acid chloride at this point. And then I've also got this guy, okay? So this is going to immediately fall apart because if we look at what we have, we essentially again have, it's not technically tetrahedral, but we still have a leaving group. We still have the ability to form a new pi bond. So we are going to form an oxygen sulfur pi bond, kick off our chlorine, and that's going to give us sulfur dioxide gas. Actually, that's not going to be reversible now. Okay, so that's an irreversible step because now we're making SO2 gas. So as soon as we make that, it's going to come right off of your reaction. We've made Cl minus, and we still have our protonated acid chloride. So Cl minus, while we know that it's not a very good base, this is also very, very acidic. So it's a very, very stable conjugate base that we can make there. So it's okay to use the chlorine in this case, and that's going to get us to our final acid chloride. So this gas formation is what's pulling us to the product in this case, because as that comes off of your reaction, you're pulling all the equilibrium towards that final product step. Alrighty. So then we've got the Fischer esterification. So the Fischer is a really handy reaction. I'm just going to do it with ethanol here. Okay, so just like in previous times, we've got an acid. The first thing that we should do is to protonate that carbonyl. That's going to make a really nice, strong electrophile for us to use with our weak nucleophile alcohol. That can attack that carbonyl, move electrons up. Then I get to this tetrahedral intermediate. So at this point, my best leaving group is the piece that I just put on. So it's just like in the acetal formation, in the hydrolysis reactions that we've been talking about with carboxylic acid derivatives. If this is your best leaving group, that's going to go right back to the beginning. So we need to make one of these a better leaving group so that we can progress the reaction forward. And just as always, because these are in equilibrium, we have constant kind of like shift back and forth between them. And it's only when they start getting to the end that you can really start to kind of push equilibrium one way or the other. But it's just a numbers game really in terms of how many molecules can you have. And then eventually you'll start to have some that shift over into the product side, and then you can start doing something about it, which we'll talk about in just a minute. Okay, so we can get another ethanol to go grab that proton for us. To get us to a neutral intermediate. So we're kind of going, plus neutral, plus neutral. And then we need to make a better leaving group. So we can use that just recently protonated alcohol. And notice how this is really catalytic. So we don't need a lot of acid here. We just need a couple protons really. Okay, so now we've made ourselves a really good leaving group. So now we're good to reform the carbonyl. Get to our protonated ester. And then we can bring in another ethanol to deprotonate that. and get to our final product. And we've also made water along the way, right? In this step right here. So let's add a little over here. So that water, again, just kind of like the acetal mechanisms, the water here is really important because we can remove that water from the reaction and draw the equilibrium towards the products. Okay, so we can kind of think about remove water here, you know, whether that's adding in an absorbent or maybe doing like a Dean Stark trap or something like that to help you drive that equilibrium to product. But it's a very similar process as the acetal mechanisms. Alrighty, so hopefully this was helpful, and I will be posting another video on acid chlorides. So check that out as well, and have a good one. Let me know if you have any questions.